talk about the atoms. We're going to talk about how atoms come together to form molecules, and then how molecules basically form these tissues which form the cells, right? So we talked a little bit about tissues already. So we're going to go back now and talk about atoms. And this whole chapter is basically how atoms bond together to form molecules. And then those molecules, again, will make up these tissues. So first of all, an atom. What if you had to define an atom, what an atom is, what would you say? It's the smallest and simplest level of organization. And more so, an atom cannot be broken apart by any chemical means, only mechanically, right? So mechanically, atoms can, we can put them in a particle accelerator, we can smash them together and they can break apart. But what is there to break apart? What makes up an atom? What are the three components? Good, neutrons, electrons, and what was the last one?
Protons.
Protons, right. So protons are, what charge do they have?
Positive.
Positive. Neutrons?
Negative.
Ah, I tricked you. I did the neutral one first.
Yeah.
Neutrons don't have a charge, but electrons are negatively charged, right? So protons have positive charge, neutrons have no charge, they're neutral, and electrons are negatively charged. Okay, so tell me about the structure of the atom. The atom has a central core called the what?
Nucleus.
Nucleus. What components are found, of the three that we mentioned, what components are found in the nucleus of the atom? Protons and neutrons, right. So we have protons and neutrons in the nucleus of the atom. Surrounding the atom, we have then our electrons, right. So the electrons surround the atom. Okay, so we're going to talk more about that. So when we look at an atom, we can determine its mass, how heavy it is, by looking at what two components?
Protons and neutrons.
Yeah, protons and neutrons. All the weight of an atom, its mass, its atomic mass, is in the nucleus. So the number of protons and the number of neutrons that an atom has will give you its atomic mass, okay? Again, all this is in the notes, and we're going to go over it again, okay? So this is just the first time through. So this electrons, again, they're going to surround the atom, but the electron weight is really very negligible. It comes into play a little bit, which is why if you look at a periodic table, and I think in the other room there was one, I'll show you, the weight of an atom a lot of times isn't just a number. There's also like a few numbers after the decimal point, because the electrons count a little, but it's primarily the protons and the neutrons that make up the weight. Okay, so atomic mass, protons and neutrons. There's one other thing, there's an atomic number, and the atomic number of an atom tells us what? Tells us the number of what of those three components?
Protons.
Good, protons. The atomic number tells us the number of protons. Okay, so I'm going to give an example here. Very simple example. Hydrogen. Okay, hydrogen. Hydrogen is very small as an atom, as far as an atom is concerned. Hydrogen contains one proton in its nucleus. Okay, which means its atomic number is 1. It doesn't have any neutrons, so this is something sometimes that confuses people. An atom doesn't have to have the same number of protons and neutrons, but atoms do have to have the same number of protons and electrons. Why? Because protons are positively charged, electrons are negatively charged. An atom has to be electrically neutral when it's not bonded with any other atoms, okay? So when it's in its native state, I guess you could call it, when it's by itself, it's electrically neutral. Okay, so hydrogen has one proton and one neutron. How many electrons does it then have? One. Because protons, we have one positive charge, we have to have one negative charge. That neutralizes the atom. Okay, that makes sense? Now, the proton number tells us, that's our atomic number. And our atomic number specifically tells us how many protons we have. But indirectly, it tells us how many electrons we have. Because protons and electrons have to equal out. Does that make sense? Does anybody have a question about that so far? We're gonna do more as we go. Okay, so hydrogen would have one electron. And now it's electrically neutral. Okay, let's look at carbon. Okay, carbon, actually it has different forms, but one of the more common forms of carbon is carbon 12. The 12 tells us the weight, the mass. So how many protons does carbon have? How many protons and how many how many neutrons does it have? It's carbon 12, so it has to have 6 of each. 6 protons, 6 neutrons, right? Because when you add 6 and 6, that gives us our weight, our mass, which is 12. When I say carbon 12, it's got to have a mass of 12. So what gives it a mass of 12? 6 protons, 6 neutrons. Okay, so what's its atomic number? You have 2 choices, they're the same. They're 6, right? Because, why? Because we have 6 protons. That tells us our atomic number. So that also tells us we have how many electrons? 6. Now, here's the next part that we're going to kind of advance to. Electrons are usually arranged in what we call shells around the nucleus. And we're not going to get into like the specific configurations here. We're going to keep it very basic because this isn't chemistry. This isn't a general chemistry class. But the first shell in any atom can hold, I'm kind of checking you guys and your knowledge too, but how many electrons can the first shell of any atom hold? 2. Good, you remember that. Every shell thereafter can hold how many? 8. Good. So if carbon has an atomic number of 6, meaning we have 6 protons, and you already told me it has to have 6 electrons, how many electrons do we put in the first shell? How many?
2.
2, right? And how many we have left?
4.
4. Very good. So the second shell will hold 4 electrons, even though it has the ability to hold how many more? 4 more, right. Okay, so these electrons that we have in this outermost shell are called our valence electrons because they can participate in chemical bonding, okay? So these valence electrons are going to be involved with bonding with other atoms because, okay, I don't want to talk too much about relationships like I did. Remember how I taught? I don't know, when you talk about, they don't call chemistry when you talk about relationships for nothing, right? Because there's a lot of analogies you can use in chemistry when it has to do with relationships. Here's my first one. Okay, so people, just like atoms, are stable when they're alone. Well, hopefully, right? They're neutral electrically, just like carbon over here, right? No, not too much positive, not too much negative, just right? Okay, but we know that truly in life, we really want to be complete. We want our outer shells to be complete, right? So we're going to go out there on a limb, we're going to bond with other atoms, people, whatever, right? And of course that can change, how much positive, how much negative we have. Okay, so that's pretty much what chemical bonding is about. You're like, okay, lady, she's lost it. All right.
You should have just said it.
Huh?
You should have just did it.
Just did it? What do you mean? Oh, didn't I help him? Okay, well, I'm I'm gonna work into it slowly because this is only day 2 and you guys are gonna really worry about me. You're gonna be like, man, she must have had bad breakup. No, it's not. No, it's not that. It's just that it's really relatable. A lot of people can understand chemistry in these terms because it's relatable. Everybody has relationships. So anyhow, I'm fine. If I made it through a burglary, I'm fine. Okay, so now I want to talk a little bit about chemical bonds. And we're going to see how these electrons play a role, okay? So there are 4 types of bonds that we're going to talk about, starting with the most complicated, well not I shouldn't say complicated, that's not the one that I want to say. Starting with the strongest and most stable type of bonding arrangement. And that is the nonpolar covalent bond. Now I want to tell you, anytime you see the word covalent, anytime you see the word covalent, you should be thinking to yourself that there is sharing of electrons. The term nonpolar versus polar, which we'll talk about next, refers to whether or not we're sharing electrons completely equally or slightly unequally, okay? So nonpolar covalent bonds, an example of this would be CH4, which is methane. CH4 means that we have 1 carbon and 4 hydrogens. And I can tell you that carbon is an atom that does tend to be in this type of bonding relationship with other atoms, nonpolar covalent. And here's the reason why, okay? In nonpolar covalent bonding, electrons are being shared completely equally. Okay, so when you look at this, okay, you already told me, okay, that carbon has 4 electrons in its outermost shell. You told me it needs how many more? 4 more, right? So carbon is basically half full or half empty, however you want to look at it. So whichever atoms that bonds to it, it's going to be sharing half of its electrons with. That's what makes it so stable of a bonder. This is like, you know, this is like the guy who's ready to settle down, who's like, you know, this is it. This is all, I'm ready to settle down, bonding, I'm going to share everything equally, very stable, very good bonding relationship, right? Perfect. When you think about it, in relationships, when things are shared equally between 2 people, or in this case, between 2 atoms, it's going to be very, very stable and strong. And actually, a lot of our macromolecules that we're going to talk about, glucose and like triglycerides, all that stuff, pretty much most of the bonds you're going to find there are going to be nonpolar covalent because these are really stable molecules. Okay, so let's look at how this bonding would occur. So here's carbon. Again, remember its atomic number? What was it?
6.
6. So that means it has how many 6 of what? It means it has 6 what?
Protons.
Protons, and indirectly 6 electrons, right? So how many in the first shell again?
2.
2. And in the second shell, we have 4. Now, CH4 means we have 1 carbon, 4 hydrogens. So do you remember what the atomic number of hydrogen was? It was 1. Because remember over here, hydrogen has 1 proton. It means it has 1 electron also. Okay, so here's hydrogen's electron. Oh, that's the first time that happened today. Usually it happens much earlier in the day. This is like the worst ever. This case is so busted apart, it's not even funny. I mean, I'm glad for the case. Okay, so we've got 4 hydrogens, each one having an electron here. Okay, so what happens is, how many electrons could hydrogen hold in this shell?
2.
2. But it has 1, so it needs what fraction of its electrons? it needs half its electrons. Carbon has 4, it needs how many? 4, which means it needs half of its electrons to make itself complete, right? So, just like in Jerry Maguire, hydrogen wants to be complete, you complete me, and carbon is the same, you know, you complete me, right? So, each one of these is going to share half of their electrons. Okay, does this make sense to you guys?
Slowly.
That's okay. It takes time to take the dust off the cobwebs sometimes. Okay, so I'm going to draw these little circles which indicates a bond. Okay. So what happens is that, and it's not like, you know, this is a static diagram, but, you know, we've got carbon with 4 of its original electrons. It's 4 original electrons, plus now it has acquired 4 more electrons that it's sharing with the 4 hydrogens. So now carbon has in its outer shell 8 electrons, and it's fulfilled, it's filled. The hydrogen, the same. It had its original electron, but now each hydrogen is sharing one of the electrons with carbon, which means that now hydrogen has 2 electrons in its outer shell, and it's complete. And so this is very stable because each atom is sharing half of its electrons with the other. Okay, let's try another one. Oxygen. O2. Oxygen has an atomic number of 8. So what does it have 8 of? Directly, it has 8 protons. So it has 8 protons in its outer shell, or I'm sorry, in its nucleus. And it has 8 electrons in the subsequent shells. How many in the first?
2.
2. How many in the second?
6.
6. Okay. Now, this is O2, which means we have another oxygen with the same situation. All right, so each oxygen needs how many electrons in its outer shell? Each one. They have 6. How many can they hold?
2.
8. So that each one needs 2, right? So, all right, you know, we have 2 out of 8. That would give us, if we reduce that fraction, it would give us 1/4, right? So each one of these oxygens is going to share 1/4 of its electrons with the other. So they each need the same amount, and that's why they bond in a nonpolar covalent way, because they're sharing the same ratio of electrons with each other. So here we have, in this case, a double bond, because each oxygen is sharing 2 pairs of electrons with the other. So that's a double bond. This is a single bond here. So we have oxygen. First one here had 6 of its originals, 1, 2, 3, 4, 5, 6 electrons, and it's sharing 2 from the other oxygen, 7, 8. Likewise, this oxygen, 1, 2, 3, 4, 5, 6, it's sharing 2, 7, 8. So now each one has a full outer shell, but the electrons are being shared completely equally because they're sharing the same ratio. Each one is sharing 1/4 of its electrons. Any questions about that? Okay, so next we have polar covalent bonding. And when you hear the word polar, this means that electrons are not being shared equally. They're being shared though, because it's still covalent bonding, but it is slightly unequal sharing. But you're still sharing. But but this is a less stable arrangement. It's a less stable arrangement. You know, again, if you have a relationship where, you know, one person might be investing a little bit more than the other person, and the other person feels a little bit put off, you're gonna have sort of a little bit less of a stable arrangement, right? One person's gonna feel like, I'm not, you know, I'm putting so much in, and the other person's not giving me as much. They're taking from me. That's kind of what happens here. The one molecule for our purposes, since this is physiology and this is such an important molecule, is water. Water has a polar covalent bonding relationship between oxygen and hydrogen. So we have oxygen. Again, its atomic number was what? Well, that's kind of unfair one, but yeah, oxygen, its atomic number was 8, which means it has 8 protons and 8 electrons. So again, we have how many in the first shell?
2.
2. How many in the second shell?
6.
Right. It has 6 in the outer shell. So it needs 2 more, right? As we said before, what fraction of its electrons does it need? It needs 2 out of 8, which is 1/4. Okay, it only needs 1/4 of its electrons. So 1/4, I'm gonna put there. Hydrogen, we've got 2 of them because it's H2O. Its atomic number is 1, so it has 1 electron. And how many more does it need? 1. And so it's going to be sharing half of its electrons. Hydrogen is investing a lot more into this bonding relationship than oxygen is, right? Oxygen's only sharing 1/4 of its electrons, but hydrogen is the one that's really investing in this. It's sharing a half of its electrons, okay? So when this bond happens, when we have this bonding relationship occurring, at certain moments, which we call a dipole moment, because at certain moments of time, we establish slight poles. What's a pole? Things that are opposite. In this case, we're talking about a slightly positive pole and a slightly negative pole. So if oxygen's not investing as much as hydrogen, and it's basically going to take more from hydrogen, what's going to happen is again, at certain moments, the electron from hydrogen is going to be pulled towards the oxygen, okay? So that happens, right? You're in a relationship with somebody, you're giving so much to them, and they're not giving as much to you, and still, it's like when you're good to somebody, then they start to want to take advantage of that, and they want more, right? That's the same idea here. You following me on these analogies? A little too, okay. Look, I don't want to get too like days of our lives, but regardless, okay, so what's going to happen to the charge on hydrogen if oxygen pulls on its electron a little bit? That means that hydrogen, still having 1 proton, right, is losing a little bit of its electron, so its charge will become slightly what? Slightly positive, because you're losing a little bit of the electron because oxygen is tugging on it at certain moments, right? So hydrogen still has its proton, but its electron is getting tugged away from it, so it still has a positive charge, but it's just slightly positive. So this upside down fish symbol means partial. It means it's got a partially positive charge, partial. Oxygen, on the other hand, having its 8 protons, now is taking a little bit more of that electron from hydrogen. It's going to be slightly negative. Does that make sense to you? Slightly positive, slightly negative. And that is why it's not quite as stable of a bonding arrangement. However, this is really a great bonding arrangement to allow water to have all the amazing properties it does, to make it a great solvent in our bodies. Why so much of our bodies is water is because of this. And in lecture, we're going to talk about some of the properties of water that is afforded it. In other words, I guess it's conferred upon it, or that is given to it because of this polar covalent bonding relationship. So, do you have any questions so far about nonpolar covalent and polar covalent bonding? Anything? Okay, two other types of bonds we're going to talk about, and as we continue to go down the line, these bonds get weaker and weaker. The next type we're going to talk about is ionic bonding. And this is usually going to be seen with things that can become charged. So an ion is a charged particle, and in our bodies, we have tons of ions. That's why you drink Gatorade, right? Your electrolytes are basically ions. What are ions? Things like sodium, Na+, potassium, K+, chloride, Cl-, calcium, Ca+. All of these things are ions because they're charged particles. And how do we get ions? We get them first from ionic bonding, and then later by water dissolving that compound and leaving the ions free in the body, because they don't usually come back together once they've been dissolved unless you dehydrate the body. It's kind of like this. If you've had, sodium chloride, for example, is an ionically bonded compound. If you put it into water, are you going to be able to get that salt crystal back? No, unless if you dehydrate all of the water, it's possible that those can find each other again. And then you might have some salt crystals on the bottom of your pot. But in the body, once an ionic compound is dissolved and you separate like Na+ from Cl-, it's not going to come back together because you have all that water that's in there. So how do we get ions in the first place? We get it through ionic bonding. Again, NaCl is the main example I think everybody uses when they first talk about ionic bonding. So NaCl is made up of sodium and chlorine, okay? So sodium has an atomic number, you might need to look in your notes. I think isn't it 11? And chlorine is 17, or am I opposite? Sodium's 11. Sodium's 11. Okay, so sodium's 11, so that means we have 11 protons and 11 electrons. How many electrons in the first shell?
2.
2. How many in the second?
8.
Okay, and how many in the third?
1.
Just 1, right. Chlorine has an atomic number of 17. So how many in the first shell?
2.
Second shell?
8.
Third?
7.
7. All right, so ionically bonded compounds get that way because usually you've got one atom which has an almost completely empty outer shell that bonds with an atom that has an almost completely full outer shell. So in this case, sodium's almost empty. Chlorine is almost full. So what happens is it's just really easier for sodium just to give up its electron, give it to chlorine. Chlorine then will have 8 electrons in its outer shell, and sodium's outer shell will go away, and that other shell will be the outermost one. So you take the electron from sodium, you give it to chlorine, and then what you end up with is sodium only having the 2 shells, and the outermost shell is full. Okay, but we know sodium's atomic number is still 11, so So it still has 11 protons, but now it only has 10 electrons. So we're positive by 1, right? We have Na plus. And then the chlorine, which gains the electron, now will have 3 shells, and its outermost shell will contain 8 electrons. And again, chlorine's atomic number was 17, so it still has 17 protons, but how many electrons does it have now?
16. 18.
It has 18, right? So it has 8, 8 in the second shell, 2 in the first, that's 10, and then 8 in the last shell, so it's 18. So we're negative by 1, right? So now, instead of chlorine, we have a chloride ion, which is Cl minus. So what holds these two together? They don't share anything. They just like each other, you know, because they're opposites, and that's what holds them together. But we all know what happens in a relationship like that, right?
Yeah.
As soon as you go someplace, like you go to, you know, the club or something, and there's somebody else, like, you know, who's attractive, you know, this isn't too strong, right? And, you know, they get separated pretty easily. They do. Now, how are they going to get separated in physiology? Water. Water breaks it up. It's like the universal homewrecker. It just comes in, and it goes after. Sorry, I had to laugh at that one too. That one just came out. Anyhow, all right, so it breaks up the sodium and the chlorine. Now, how does it do this? I'll explain. Okay, so water, we know, has like a slight negative charge on the oxygen and a slight positive charge on the hydrogen. So the slight negative charge on the oxygen will be attracted to this positively charged ion, sodium, and will form a water circle around the sodium, which we call a hydration sphere. Okay, it's a water circle. And then the slightly positively charged, bless you, hydrogen will orient itself around the negatively charged chloride and form another water circle or hydration sphere. And that's how water dissolves an ionic compound like sodium chloride. It separates it that way. And I have a diagram in the notes. I'm going to show it to you so that you'll see. But yeah, so this is not a very stable relationship. And once these are separated, again, by water, usually they don't come back together unless the water just completely dehydrates. You know, it goes away and then maybe they can come back together again. Okay, so any questions about that? So some terminology, a positively charged ion is known as a cation, and I always remember it's positive because a T, if you make it without the little curve, it's like a plus sign. And then the negatively charged ion is known as an anion, which I remember because the second letter is an N, so it's negative anion. All right, guys, we're rounding home base here, almost done, and we'll go back in, take a look at the notes, and just finish up the first part. I think. Well, I don't know if we'll see how you get hydrogen bonds. Do you have any questions though about this? I don't want you to be completely lost at this point. All right, so last type of bonding, which is actually the weakest bond type, but is really very important bond type that again allows water to have a lot of very interesting properties that we'll talk about and that are listed in the notes. But hydrogen bonding specifically occurs between neighboring water molecules. So try not to get this confused. I could ask you a question and say, what kind of bonding happens between atoms within a water molecule? That would be polar covalent. because that's the type of bonding that happens between hydrogen and oxygen. If I ask you what kind of bonding happens between neighboring water molecules, it will be hydrogen. It will be hydrogen bonding, right? So here's what happens. We have oxygen and hydrogen. Just gonna draw out a couple of water molecules here. And I'm just gonna put their charges. I'm not gonna draw out any electrons or anything. Okay, so oxygen is slightly negative and the hydrogen is slightly positive. So what happens is we have these very weak attractions between the slight negative charge and the slight positive charge. Why this is so weak is because when you have polar covalent bonding like this, generally this is not going to stay this way. It's going to change. This is very dynamic. It's not static. And as I mentioned earlier, only at certain moments, called a dipole moment, will you have these two poles established. So hydrogen bonds can very easily break and then reform again, depending on the situation. So here we have our little hydrogen bonds, which are always, just so that you know, if you ever look at a diagram, hydrogen bonds are always indicated by a dotted line because it's not a solid bond, it's a very weak attraction. It's really not a bond at all, in fact. Just a weak attraction. So again, these can break and reform. This is why water, if you look at it, you know, in a glass, it'll take on the shape of the glass if you don't put any energy into it, if you don't like move the glass around. But if you do move the glass around, if you spill some water out, it'll change its shape, right? It won't look like the glass anymore. It'll look flat like the table, because the hydrogen bonds between the water molecules can break apart and reform in different ways and gives it a different shape. Do you have any questions at all? Okay, ready to migrate back over to the other room? This is like the Sisterhood of the Traveling Pants, only with men. Yeah, because it's like